לא משנה לי,
לא,
because it's going to be filmed from later. Okay. I'm happy to introduce Michael Zibulevsky from Technion. Actually moved to Jerusalem, to live in Jerusalem, so we see him around here. Thank you for coming. Thank you.
כן.
Okay. The topic of lecture today is an optimization method, actually framework for so-called very large-scale optimization. Very large scale mean probably millions of variables. So those problems become more. They were always important in fields like partial differential equations and so on, and they become more and more important now with signal image processing, vision, tomography, and so on, where variables may be, for example, pixels of three-dimensional volume. If you pixelize 1,000 by 1,000 by 1,000, you easily get to million variables. And work with large databases, with pattern recognition, support vector machines, so on and so on. In many places we meet such problems with a very large number of variables. And then traditional methods in optimization become less relevant, and people in optimization step back in some sense in order to go forward. And I will explain now what do I mean. Suppose we have a function. I draw level sets, function of two variables. And there are level sets. And everybody, every engineer and physicist, in order to find minimum of this function, will say, let's do gradient descent, steepest descent. Because gradients show in the steepest direction of descent. I'm staying here, and gradient is orthogonal to the level line, and it goes here. And for example, clever methods may do one-dimensional optimization in direction of gradient. So they do exact optimization. I get to some new level set, and new gradient will be even orthogonal to my previous direction because I optimized, I did everything in this direction. And very fast I will get to mean. But sometimes functions have such level sets, long level sets. And what will happen then? Gradient will start orthogonally, and then orthogonally to the next, and then it starts zigzagging. It's very known, it's very basic part in optimization. And one can express this mathematically if we approximate this function as quadratic function, or say this is quadratic function, and in quadratic form, okay, let's write Taylor expansion. F of x k current iterate plus some shift d is f of xk plus gradient of f k transpose d plus 1/2 d transpose Hessian matrix d. Okay. So this Hessian matrix defines how those level sets look. And if largest and smallest eigenvalue of those matrices were close to each other, we would have such level set. If they are very distinct, we will have this narrow value. And about gradient, it's known that it's linear convergence rate. So the discrepancy between function value and optimal value decreases mainly linearly with coefficients. It's 1 minus lambda mean by lambda max, ratio of eigenvalues, absolute value. So if this ratio is 1/1000, then we will have this 0.999, and our discrepancy will reduce very slowly. So what people do in classic optimization? They say gradient method is like using first order model, approximating our functions with this linear function and going to direction of descent of this linear function. Let's do one more term in Taylor expansion, and let's at every step minimize quadratic model. And if there is a quadratic function of many variables, then derivative of quadratic function is linear as a function of one variable, yes, if we do derivative. So finally we need to minimize quadratic function to solve a system of linear equations which happens to be a system with this matrix, with matrix ratio. And this is the idea of Newton method, find minimum of quadratic model, and also use this direction, for example, as line search, do one-dimensional optimization. And it's very good, it's very recommended until you have 1,000 or maybe several thousand of variables. To solve general system of equations which is much more than 10,000 variables is problematic even in modern computers. I'm not saying about million variables. Even to store a matrix million by million, I guess it comes to the boundary of possibility of modern computers. And also there are other methods, so-called quasi-Newton, which even not compute hashing explicitly, but approximate it based on several gradients on the way how our algorithm worked, and even build inverse hashing in process. But still, with millions of variables, we cannot use it. And that's why there is a word, conjugate gradient, and methods built around it. And I can move camera here. And the framework I will present today, SESOP, it's actually based on some very basic properties of so-called conjugate gradient methods, which brings advantage of both. They have complexity of usual gradient, about usual gradient descent, but convergence properties much faster than steepest descent. Okay. Okay, problem formulation I already told, many applications, and this I already told. This is a general expression after works of Arkady Nemirovsky, who studied in 70s complexity of convex optimization problems. What the best algorithm, which we even might not know, cannot do better than. And he claimed that in worst case, for the worst convex function, the discrepancy cannot decrease faster than 1 over k squared, where k is iteration count. It's actually, in some sense, when condition number, when ratio between lambda min and lambda max is good, gradient descent gives much better than this. But when ratio is very bad, we don't build on linear convergence. Say here is few more nines in this expression. Then this formula becomes practical. And we will bring methods which takes actually advantage of two modes. Also this formula also significantly improves convergence rate of gradients. And here is the method. The method is extremely simple. Extremely simple. We just, at some point k, after iteration k, we stay at some point and we have gradient of our objective function at this point. And we have also directions of several previous steps which we already used in our method. xk minus 1, xk minus 1 minus xk minus 2, and so on. And we just minimize our objective function over subspace, affine subspace, spanned by those vectors. And that's all. It's all description of the vector. You may ask questions at this point. Okay.
So when the condition number is bad, you typically stay on the very same direction in each of these iterations, meaning the subspace is actually basically one vector, really.
It's difficult to say. I will tell you, for example, conjugate gradient methods, which will explain on the way. It is known in n steps, where n dimension of the problem, to achieve accurate solution if you have very accurate computer. So your argument, and it does exactly this.
Right, but n is very big. You never reach this n. So
Okay,
most of the time you step.
This is why your argument is not complete. With in n steps you do achieve solution. Okay, but we will return to this maybe later.
In n steps you're spanning entire Rn, so obviously you're
Okay, so it means that it's expanding, it's not staying in subspace, in narrow subspace.
What I'm saying is that I'm not sure that the subspace is containing more than one single vector.
This is what I'm explaining. At least after n steps, it contains n different independent vectors.
You go at least one more each step.
Yes,
You can't go more than that.
Right, but all these vectors,
They are maybe close,
they're very close,
but they're expanding, and it's clever to expand. Okay, and how will we do it technically? We built a matrix which columns contains those directions. And we say that our x is xk plus this matrix multiplied by some weights alpha. So we should minimize, in order to minimize in affine subspace, we minimize this function of several variables. And in practice, number of variables, we only keep several last steps, say 3 last steps or 9 last steps. So we do minimization problem is in very small number of variables. We can use Newton method for that optimization, and it's relatively easy. And then we go just to the next one.
Actually, conjugate gradients would typically search for the most different vectors than the ones you've been moving so far.
We will come to conjugate gradient. Let me
Seems that-
flow. I will have slide on conjugate gradient, and we will return.
But you're using the very same direction.
Discussion.
So
I will come to this later. Just remember your question. Okay, and one can say that actually doing optimization in subspace may be numerically more challenging than doing just a line search that most optimization methods use. And we say that if a function have such structure, you have some linear mapping A, very large matrix A, and then you take some nonlinear function from this, or even some simple, quadratic function. Then to compute optimization in subspace is relatively cheap. And if you will look on applications, almost in every application you have such structure, almost everywhere. In those I mentioned, computer tomography, deblurring, denoising, support vector machine, everywhere you have such type of structure. So what you do then, for example, I want to compute AX, and I already had AXK, previous A. So it's X is XK plus, what was there? sum of alpha I pi, yes? Just a second. Let's go to this.
The line
Written up
above.
there.
The line above the height.
Ah, okay, yes. So, and I substitute, I look AX, so it should compute AP alpha, yes? So, and when I open AP alpha, I find that I should multiply matrix A by columns of P. But my columns of P, every iteration I get to only one new column of P. So I already collected those products like vectors VI. So when I do my computation in subspace, I don't have this multiplication by huge matrix A, so it's not terrible to do this subspace optimization. Okay. And actually, in order to have this nice theoretical property, that our discrepancy is Lipschitz constant of gradient. This Lipschitz constant of gradient, you can think about largest eigenvalue of Hessian, something like this. And here is distance from original point to actual solution. Our estimate, our upper bound, for example, if you don't know distance, and this is square of number of iterations. In order to get these theoretical results, we need two additional directions. And this follows from earlier works of Arkady Nemirovsky and Yuri Nesterov. Some works of most earliest of Arkady Nemirovsky and some the joint works. So you have this direction from current point to the origin and some clever weighted sum of gradients. So if we add to our direction those two, we have this nice theoretical results. But what we found in practice, in our numerical experiments, it doesn't improve practical behavior. Maybe one should look for a challenging example. We didn't find it, where those theoretical additions help us.
So this is the same rate for Nemirovsky.
Yes, this what knows, who knows Nesterov method, who knows FISTA, those are the same number. Our advantage is that we are not only worst case optimal, we have some other optimality properties which are some, and by the way, this is also property of conjugate gradient method, which I will mention soon, but conjugate gradient methods has more interesting and important properties of convergence, which those methods lose and we get them back.
So I just want one question. So where does the M come into the rate?
Actually, there is no M. You're right. It's enough to use one previous direction, and you already have this complexity. Okay. And now link to conjugate gradient methods. So original conjugate gradient is to minimize quadratic function. Here is an example of quadratic function. And how it goes, you compute some direction of conjugate gradient and perform line search. How one computes direction? It's a weighted combination of current gradient and previous direction. In this way, conjugate gradient works. And there is some explicit formula how to choose this weight for quadratic functions. And there is a whole theory of Krylov subspaces and so on, why this is working. But I can say we can find way to conjugate gradient a bit differently than classical explanation, but it comes from classical explanation. We can take direction of current gradient and direction of previous step, and we have quadratic function in linear in affine subspace of those two directions. If one say, I want just minimize my objective function in this two-dimensional subspace, he will get this better. So this is another look. So what we do in SESOP, we do like what conjugate gradient does for quadratic functions. But there is a very basic property of conjugate gradient, it's so-called expanding manifold property. It happens that by this simple action, actually we optimize our objective function in subspace of current gradient, previous direction, which we did explicitly, but also all other previous directions. And this is the optimality of conjugate gradient methods. Really finds the best you can find in a combination of all information in subspace of all gradients and direction you have until now and your current gradient. And this what SESOP would do. The only thing when people classically expand conjugate gradient method to non-quadratic functions, they say, let's go to the same principle. We do line search in our new direction, and direction we will find as the weighted sum of current gradient and previous direction, and use the formula which is very close related to formula, it's equivalent formula for quadratic case, just taken from quadratic approximation of the function. And we say a bit differently. We don't stick with this formula, we stick with the principle. Do optimization in subspace of several directions. So it's clear that in case of non-quadratic function it will be different, and we observe also in practice that empirically behaves better. And also it provides theoretical property for nonlinear case, which conjugate gradient just doesn't. Nonlinear conjugate gradient just doesn't. And after that, after this very basic part, few additional accelerations which people use in other methods. For example, if we can approximately to compute inverse of Hessian of our function. So if we change variables in such clever way that our level sets will become around, it will not be narrow anymore, and run conjugate gradient on this new system, it will converge very fast. Roughly speaking, if you have an approximation, which I call W, of inverse Hessian, in framework of SESOP, you do a very simple thing. Instead of new direction gradient, except of you have several last direction of steps and new gradient. Instead of new gradient, you put just W multiplied by new gradient, and this is preconditioning. And when you have such a matrix, for example, if your matrix Hessian is very diagonally dominated, then you just use inverse of diagonal part of H. It helps. But there are also many other cases when approximate inverse exists. And we use it, and it helps. And there are some other tricks how accelerate gradient descent. But by the way, the previous way, the previous principle also accelerates gradient descent. Textbooks in optimization start that the most primitive methods of optimization is coordinate descent. And it was historically really, I think, the first optimization method implemented in computers. If I am not wrong, in Second World War, when they do artillery correction or something like this, it was coordinate descent. You have function of 10 variables. You minimize by first variable. Tune. You have 10 handles. Yeah? You tune first handle, to find the minimum, then the second handle, then third handle, and then you go around. And this is a very primitive method, and every textbook on optimization starts. Of course, we know coordinate descent, and now we will show you better methods. Interestingly, when you come to very large problems in many applications, coordinate descent is the best. It's better than gradient descent. It's the best of simple methods. And for example, in tomography or in sparse signal representations, one can find that coordinate descent is really better than gradient descent. The only thing with coordinate descent, if you have function which you have some matrix vector multiplication like fast Fourier transform, then coordinate descent destroys your nice structure. And because of this, Mickey Elad, from my colleague from Technion, who is working on sparse signals, he suggested to use this so-called parallel coordinate descent. We do minimization in first coordinate and shift back. Do in second coordinate and shift back. Do in third coordinate and so on. And then we remember those positions and choose this like our new direction, and do also one-dimensional minimization. It happens to be very efficient for sparse signal representation and so on. And we say, instead of new gradient, we use this direction as a new direction of SESOP and also previous steps. And this accelerates significantly. One more very popular technique for very large problems is called so-called separate surrogate functions, and it comes close, but it's sourced by a so-called expectation maximization algorithm, EM, that people use in statistics and in many engineering applications. So, what is idea? We have our objective function, f of x. But suppose that we have other simple the other function which is simple for us to minimize explicitly. And we build this function in the way, for example, this is my f of x, and I am staying at some point. I built another function, oops, maybe not very successful. I built, this is f, this is my point xk, and this is my function q. So function q modulates q of two arguments, x and xk. Q is everywhere larger than f, except of the point xk where they are equivalent. So if I am able analytically to minimize q and I get any other point, my picture is very not successful. Let's do it in this way. And I get point of minimum of q, I'm sure that my f is also smaller than it was originally. Why? It's written in this inequality. So when I stay at point xk, my q is the same as xk. By minimization, I decreased q, but I know that q modulates f. So I definitely will decrease my f. And again, in recent several years, this approach will become very popular in sparse function approximation. And it was developed for the case when my f of x is combination of least square term and some penalty term, separable terms, for example, sum of absolute values of variables. When I have such combination, I can open the quadratic function, which is relatively complicated, because it has multiplication by some general matrix, and substitute it by separable quadratic function, or even by a quadratic function with round level sets. I would say if this is my quadratic function, and I'm staying at some point let's do around center, around minimum. So if I substitute it by function with such level sets, it will be smaller. Sorry, I should think about this explanation, about graphical explanation. Let's for a second go to formal explanation. So I can open, like in Taylor expansion, only a quadratic term, only this term. So it's gradient of function, value of function psi plus gradient transposed by x minus xk plus this will be Hessian. Believe me that if I open this as quadratic function, this quadratic term will have a transpose A. So then if I substitute Hessian by some diagonal matrix which is larger than Hessian, and here I should say one word, what is matrix inequality? What does it mean, one matrix larger than other matrix?
This is for each vector x. Lambda xx double is greater than 88x.
Yes, you're right, and in the same way, to say that lambda minus A transpose A is positive definite matrix. Okay, so if you have such lambda, then we have a quadratic function which, like you told, is everywhere larger than my. So it's this is majorating function, but it's separable. So if I substitute it as my q, I get a function which splits in every variable. I can do independent optimization, and this so-called iterative thresholding methods, which say all such optimization actually is some analytical nonlinear expression of some variable, they become very popular. And what we did, also parallel coordinate descent, also this direction, we combined with SESOP instead of gradient, and we actually got state-of-the-art results, state-of-the-art computational results and sparse signal recovery. Okay, you are a bit tired, I guess. I have few experimental results, and I have one more mathematical part. Let's go for experimental and then return.
Can you extend SESOP to using a different loss function in the quadratic one with regularization term? Using the hinge loss with the regularization term?
If you find separable surrogate function, I guess in expectation maximization in statistics, you may have a large variety of functions, and you can try to combine SESOP with those functions. Okay. Let's show some graphs, and then if you have energy, we'll go a bit more to. So some examples from tomography, signal denoising, deblurring, and support vector machines. And we find this expression everywhere. For example, in computed tomography. Let me skip to a picture. I don't have, unfortunately, numbers. You don't see numbers of slides. Okay. If I do escape, I should see. Yeah, I was in 14. Just to show example of picture. Yeah. What tomography does. It's not so clear. For example, I have a two-dimensional image, and what I do, I put it in X-ray machine. And under every angle, I collect integral through this image, integral of density of this image. I get one-dimensional pattern, like projection, and put it as a one column of this new image. After I did, I don't know, 360 angles or 1,000 angles, I get such picture, you don't see it clearly. But this is my R, what was R in least square expression. And after 20 iterations of our method, we actually recover the original picture. Let's go back to 14. Okay.
Just one question about the example.
Yes.
It was taken from real physical projection or from mathematical simulations?
This is mathematical simulations.
So you didn't added noise or anything, or
We add the artificial noise. In this example, maybe Gaussian noise, but also we tend to add Poissonian noise, like close to real physical situations. And this example is even more interesting. The image itself was like dots. So, and we put L1 norm to recover sparse image. And here is an example how fast different methods converge. Truncated Newton I didn't explain yet. So this is Nesterov. This is the same methods with the best worst case complexity like ours. But after doing preconditioning and subspace optimization, we did much faster, and actually nonlinear conjugate gradient was pretty close to ours. It's close to FISTA. Yeah, it's not FISTA. I don't. It's not FISTA because it was not adjusted to this clever combination of two terms, sparse term, L1 norm term, and it's not FISTA yet.
So what is the size of the subspace?
Usually we have 1, 2, and up to 8.
In this example?
I don't remember. Probably 8. This is SESOP 1. Actually, 1 means only 1. By this number is.
So isn't 1 is the conjugate gradient?
It's for quadratic function it would be, but for nonlinear function it's not, because we do explicit optimization in the subspace.
So you're solving on 1D or 2D in SESOP 1?
In 2D, in current gradient and previous
So
step.
on work clock times, would it justify using SESOP 1 compared to conjugate gradients?
Say it again?
Would it be worthwhile on work clock times to...
With respect to computational time?
I'm expecting the conjugate gradients to be faster because it's a 1D optimization rather than...
This is what exactly I'm saying. If your multiplication by matrix is relatively heavy, then it's okay. It's no difference. Because you don't have this additional matrix multiplications when you do subspace optimization even in 10 dimensions. But if your matrix is fast, we often need fast matrix multiplication. Then one should reconsider. Or we do, often we do, instead of exact optimization in subspace, we do 1 Newton step in subspace. And it happens also to be pretty fast. So we just open possibility of empirical search for the best solution. But you're right. Often conjugate gradient, nonlinear conjugate gradient, it's worth to check. I agree 100%. Okay, similar objective when phi is some wavelet contourlet, some wavelet type system of functions for images. I guess in this particular case it was so-called contourlets. So we have comparison of several methods. So we have conjugate gradients, and this is conjugate gradient. This is preconditioned conjugate gradient. Just a second. This is preconditioned conjugate gradient. Actually was the best, yes. And then we continue preconditioned conjugate gradient, preconditioned SESOP with one memory size 1 with memory size 8 is the best, and then preconditioned SESOP 8. I guess it's just a second. Preconditioned SESOP 1. And then we see winners. I needed 3 plots because very different scales. But we definitely see winner parallel coordinate descent. What I told you, algorithm of Michaelat, which we combined with SESOP. And this was the fastest one. SESOP 1 and SESOP 8 gave a bit advantage. And so on and so on. Here is just example of deblurring, image deblurring, which we got again with this contourlets. This about 20 iterations, just to impress that those methods are relevant to application. Because I am on Fusion seminar, I show some nice pictures. And now I'm thinking. How much time?
Half an hour.
Huh?
Half an hour.
Oh, I was very fast.
You don't have to fill it up.
I'm thinking the two mathematical pieces, which one of them is more important? I guess the second one is more important because it brings general knowledge of optimization. There is a very important algorithm which is called truncated Newton. Let's concentrate. We had enough nice pictures. If somebody will like, in the end we will return. Because all the time we return to this formula. This is, okay.
The take-home message from the previous slide, so now if I want to really attack this problem, so you're saying FISTA and all of your techniques, they all have the same worst case, and I should just try all of them with the right conditioning, but technically in each problem someone else was going to win, right?
Sorry, you wanted comparison with FISTA, and I
No, I want practice.
This is important.
Winner.
This is important. For example, this is one of examples with FISTA. Yes, this is very practical. What was the example? Tomography. Again, tomography of such image, not of sparse image. And we see the FISTA. FISTA usually, if you plot 1 over k squared on logarithmic scale, you will see decreasing absolute values of slope. You will not see linear. And you asked the question at very good time. What we have, what Nesterov methods and FISTA don't concentrate on. If you look on gradient descendant, it has a convergence rate of this. There is a known estimate, pessimistic estimate of convergence rate of conjugate gradient, which says this. And this is very strong claim. If you have 1 over 10,000, this ratio, then you will have 1 over 100. So, will be significantly faster. And FISTA just don't care about this. And we have this asymptotic linear co-convergence. If you think that your function, actually we never proved it formally. We only say that for quadratic functions we do have this automatically, because for quadratic functions we are S conjugate gradient. Maybe one should look carefully and really go through proof, but also we observe this empirically. And our descent looks like linear. And FISTA descent looks like this. So especially when you are running for high accuracies or have very ill-posed problems, so we see an advantage of our methods. And also, in practice, when you have to recover signals from noise, you don't run to the very low, to very close to minimum, to very low gradient. You may get good solution really fast after less than 20 steps, and we see that our methods are pretty good. So it works to compress. Sometimes it's really some technical work to do this optimization in subspace, and it works to check FISTA as well and see how it goes, how this trade-off goes for your particular problem. Okay, and now back to basic optimization. Back to basics. So we have this Taylor expansion of a family, 3 terms Taylor expansion. And what the Newton method does, it minimizes it explicitly, and this is our step. But if you say, actually we don't have Hessian, but often we can implicitly multiply Hessian by any vector. So we are able to compute this quadratic function and to compute its gradient. And people say, it's very good. This is quadratic function, we have nice method, conjugate gradient. Let's minimize. We will not minimize it exactly because very large number. We will stop early. And this is called the truncated Newton method. That's the same formula which is on Blackboard. The large question is where to truncate. And there are many empirical considerations. And think that you have a function of thousands of variables, and you know that with accurate arithmetic, conjugate gradient will minimize it exactly, quadratic function. If you will truncate after 20 steps, and then run again, and then run again, after you will have total 1,000 steps, you will not minimize it. So you always in this trade-off. And we bring a very nice combination of SESOP with the idea of truncated Newton to make, not to interrupt conjugate gradient process when we truncate, to think about about history of your conjugate gradient. This is in one word. This already I told. And this is the method. This is the last intensive mathematical part of other big pictures. So we do several steps of conjugate gradient for our quadratic model. And then we do subspace optimization. So we have this truncated Newton direction, which we got with our several conjugate gradient steps. But we also use last gradient of quadratic model and previous conjugate gradient direction. If we would be in quadratic model, those two if you do just optimization in subspace with those two, we continue with legal conjugate gradient. So because we do optimization even in wider subspace, we still optimize in those. So we don't break conjugate gradient process, and this is the basic idea. And also when we go to again to truncated Newtons after we did subspace optimization, we again want to do optimization of quadratic model. We put the difference of our previous quadratic model xk plus a hat plus 1 minus xka last conjugate gradient interaction. So conjugate gradient stepped in some point. So we did like one more step of conjugate gradient. With SESOP, we imitated conjugate gradient. And this step we again include in subspace. I'm not sure that I'm clear. Just bring get it as a bold message. We use this conjugate gradient structure which yielded by SESOP step in order to continue with conjugate gradients. And then everything goes smoothly, and I just will show you graph to just justify this. So I have a function I don't remember how many variables do I write it here? 400 variables. And I show you standard truncated Newton, how it behaves if I do only one conjugate gradient, 5 conjugate gradient, so on, 40 conjugate gradient per each truncation. And you see that it behaves differently. And here is the SESOP term. You don't see difference because it's thinking about how it truncated, it memorizes state of conjugate gradient in subspace optimization of nonlinear function. Take consideration of this. And okay, it was enough mathematics. I just say that we did some experiments with linear support vector machines. Get some interesting rather numerical results. I guess it was relatively short, but too much intense. I see tired eyes. Okay, then I just finished at this point.
On the size of M, you have an intuition. Would it be always better to use bigger M's, or because you showed that M usually?
In our experiment, we of course played with this magic number like 5 or 8 was pretty good. And actually there are other methods which is called limited memory BFGS, limited memory quasi-Newton. They also have magic number of about the same size, 5 or 8. But often even 1 is good. With new problem, I would say use this number if you only do it once. But if you are going to solve it many thousands times in the future, do adjust, do tuning for this problem.
And you have the code on your someplace?
Yes, it's on my website.
I have a question. You showed the very good convergence in iterations.
Yes.
But what about computational time? I mean, a conjugate gradient iteration might be computationally simpler than your iteration.
We did this comparisons also with time. We have a paper in Signal Processing magazine, and we did comparison also time and also iterations. When matrix is heavy, we are significantly better in time. when multiplication AX. When AX is very cheap, you should consider FISTA and conjugate gradients as an alternative. And we have some funny combination also with ideas like FISTA and conjugate gradients. There are more combinations which are cheap to compute, and one more combination, as I told you, perform only 1 Newton step in subspace. It often also very good and very fast. Was it read here?
What about FISTA?
Wait.